Here is a thought experiment I want you to sit with for a moment. Imagine that somewhere in the ocean, let's say the North Pacific, let's say right now, there's an animal that has been alive for 60 years. It lives in a family group with a social structure more stable than most human marriages. It has a grandmother who remembers hunting patterns from 4 decades ago and teaches them to her grandchildren. It communicates in a dialect so specific that researchers can identify which family it belongs to just from the sound of its voice. It has been observed grieving its dead. It has been observed playing. It has been observed coordinating hunts with what can only be described as tactical intelligence. It has never, in the entire history of its species, lit a fire. This is not a hypothetical. This is an orca. And the reason I want you to think about the orca is that it is the most useful object lesson I have found for the central problem of this episode, which is not really about orcas at all. It is about Europa and Enceladus, and what we mean when we say we're looking for intelligent life, because I think we have been conflating two things that are actually separate questions. One question is there life out there? The other question is there life out there that we could detect? And those two questions, it turns out, have very different answers. The ocean is the reason why. The ocean worlds, what we actually know. Let me introduce the candidates. As of June 2026, planetary scientists have identified at least 6 bodies in our solar system that likely harbor liquid water oceans beneath their surfaces. Not ancient oceans, not evidence that water was once present billions of years ago. Liquid water, right now. Possibly hydrothermal vents on the seafloor. Possibly, and this is the word the scientists use carefully and the journalists use carelessly, possibly habitable. The 3 most compelling are Europa, Enceladus, and Titan. They are worth meeting properly. Europa is Jupiter's 4th largest moon and, in the considered opinion of most astrobiologists, the best bet for finding life in our solar system outside of Earth. It is roughly the size of Earth's moon. Its surface is a cracked sheet of ice, visually extraordinary, geologically active, covered in rust-colored ridges where the crust has shifted and refrozen. Beneath that ice, which may be anywhere from a few kilometers to 25 kilometers thick, there is a saltwater ocean, not a shallow one. Europa's ocean is estimated to contain twice the volume of all of Earth's oceans combined. Tidal forces from Jupiter's immense gravitational pull flex the moon's interior, generating heat, the same mechanism that keeps the water liquid in the absence of sunlight. There is strong evidence of plumes of water vapor venting through the ice into space. Footnote 1. NASA's Europa Clipper, launched in October 2024 and currently en route to Jupiter, will arrive in 2030 and conduct 49 close flybys, carrying a radar instrument specifically designed to peer through the ice shell. Its mass spectrometer is sensitive enough to detect a single bacterium. Footnote 2. Enceladus is smaller, only about 500 kilometers across, roughly the width of Arizona. Footnote 3. But in some ways it has given us more to work with in Europa, because it is actively venting its ocean into space through cracks in its south pole. Saturn's E-ring is largely made of Enceladus. The Cassini spacecraft, which orbited Saturn for 13 years before its intentional death dive in 2017, flew directly through those plumes multiple times and tasted what was inside. What it found has been causing quiet excitement in the astrobiology community ever since. Hydrogen gas, a signature of hydrothermal activity on the seafloor. Footnote 4. Organic molecules. Carbon dioxide, methane, and in 2023, hydrogen cyanide, a molecule that, on Earth, is considered one of the key precursors to the chemistry of life. In October 2025, reanalysis of Cassini's 2008 high-speed flyby data found new complex organic compounds, esters, alkenes, ether compounds, that had not been detected before, almost certainly originating from the ocean directly below. ESA is now studying a dedicated Enceladus mission, planned for launch in the 2040s, that would fly through the plumes and possibly land on the South Polar terrain. Footnotes 5 to 6 and 7. Enceladus, I have to say, ticks all the boxes. That is a direct quote from the ESA mission description. The world space agencies are not prone to hyperbole. When ESA says a moon ticks all the boxes, it is worth pausing. Titan is the most complicated case and the most fascinating one. Saturn's largest moon is the only moon in the solar system with a dense atmosphere, mostly nitrogen, with a methane cycle that works exactly the way Earth's water cycle works, complete with clouds, rain, rivers, and lakes. Except the rain is methane. The rivers are methane. The lakes, some of them as large as the Caspian Sea, are liquid methane and ethane. Footnote 8. For a long time, scientists thought Titan might also have a global subsurface water ocean. A December 2025 analysis of tidal perturbation data challenged that hypothesis, suggesting the global ocean may be smaller or absent, but did not rule out pockets of subsurface liquid water that could still be habitable. Footnote 9. What Titan unambiguously has is an extraordinary surface chemistry, complex organic molecules raining down from the atmosphere, accumulating on the surface, interacting with whatever water has reached it. NASA's Dragonfly mission, a rotorcraft lander scheduled to launch in 2028 and arrive in 2034, will fly between dozens of sites across Titan's surface, sampling organic chemistry at each one. Footnote 10. In August 2025, NASA researchers found that in Titan's methane and ethane lakes, simple molecules may spontaneously arrange themselves into vesicle-like structures, tiny compartments that mimic the first steps towards cell wall. Footnote 11. On Earth, we call that prebiotic chemistry. 3 worlds, all of them wet, all of them, by any reasonable definition, worth investigating seriously. The thing about fire that causes a tiny little problem. Now, here's where the orca comes back in. The question we ask about these ocean worlds, do they have life, is actually a compressed version of 2 different questions, and the compression is doing a lot of work. The first question is whether these environments could support biochemistry complex enough to produce living organisms. The second, implicit question, the one that hides inside the word life when scientists say on television, is whether they could produce life that we could detect, communicate with, or recognize as civilization. These are not the same question, and the ocean is the reason they come apart. Let's think about what intelligence requires to become detectable. On Earth, the chain looks roughly like this. Complex organisms develop social structures. Social structures enable cultural transmission of knowledge. Cultural transmission enables tool use. Tool use eventually produces fire. Fire produces metallurgy. Metallurgy produces industry. Industry produces radio transmitters. Radio transmitters produce the kind of electromagnetic signature that Drake's equation was designed to look for. Footnote 12. Every link in that chain can, in principle, exist in an ocean. Orcas have social structures. They have cultural transmission. Grandmother orcas carry hunting knowledge that is passed down through generations, and documented research shows cetaceans learn foraging techniques, dialects, and even songs from their peers. They have something that functions like rudimentary tool use. Bottlenose dolphins use sponges to protect their snouts while foraging on the seafloor. Footnote 13. The cognitive architecture is there. The social infrastructure is there. The chain breaks at fire. You cannot light a fire underwater. This is not a trivial constraint. Fire is how you smelt metal. Smelting metal is how you make tools beyond the complexity of shaped stone and bone. Without metallurgy, you do not get engines. Without engines, you do not get electricity. Without electricity, you do not get radio. Without radio, you do not produce the kind of signature that anyone looking at our solar system from 100 light years away would identify as technological civilization. This is what I mean when I say the Drake equation treats intelligence and detectability as the same filter. They are not. Intelligence is a biological question. Detectability is an engineering question. And the engineering question has a hard physical constraint that applies to any intelligence that evolves inside a sealed ocean under kilometers of ice with no access to an atmosphere in which combustion is possible. An orca has a brain-to-body ratio comparable to a chimpanzee. Its brain contains spindle neurons, the large, specialized cells associated with higher cognitive function, self-awareness, and social processing in humans and great apes. Footnote 14. It has been alive on Earth for 11 million years. It has never sent a radio signal. Not because it isn't intelligent, because the path from intelligence to radio requires a specific set of physical affordances that the ocean does not provide. Now apply that to Europa. The detection problem, or how close could something be and we'd still miss it. This section is where things get genuinely uncomfortable if you think about them long enough. Europa's ocean is right here, 600 million kilometers away at its closest approach, which, in galactic terms, is the distance between your living room, couch, and your kitchen. If Europa has microbial life in its hydrothermal vents right now, we have no way of confirming it until Europa Clipper arrives in 2030. And even then, the Clipper is not landing. It is flying past 49 times, tasting the plumes, and analyzing the surface chemistry, looking for biosignatures. Footnote 2. It is not going to radio us. If Europa has something more complex than microbes, multicellular organisms, say, equivalent to the early Cambrian fauna that exploded on Earth 500 million years ago, we have no way of knowing. The ice is in the way. The Clipper cannot see through it with the resolution required. The only way to know what is in Europa's ocean is to get into Europa's ocean, which would require drilling through somewhere between 3 and 25 kilometers of ice, and then navigating a pitch-black saltwater sea under an alien moon with no GPS and a 2-hour communication lag back to Earth. Footnote 1. We do not currently have that capability. We are developing it. It will not be ready for the foreseeable future. And here's the thing that sits underneath all of this. If there is intelligence in Europa's ocean right now, it is almost certainly aware of none of this. It has no way of knowing that 4 billion kilometers away, there is a species that discovered fire 300,000 years ago and has since developed the ability to fling metal objects across the solar system. It has no way of producing a signal that we could detect from the surface. The universe is not preventing contact between us, the ocean is. This is the version of the Fermi paradox that doesn't make it into the popular science articles, because it is not as dramatic as the Great Filter or the Dark Forest hypothesis, or any of the other solutions that assume the silence has an explanation involving extinction or concealment. The mundane explanation is this. Intelligent life may be sealed inside oceans all over the galaxy, unable to produce radio signals, invisible to any search methodology we have developed, and completely unaware that we are listening. How many ocean worlds are there? We don't know exactly, but the Kepler Space Telescope data suggests that water is extraordinarily common in the universe. Footnote 15. The conditions that produce a subsurface ocean, a rocky body in the right size range, tidal heating from a large gravitational companion, or sufficient internal radioactive decay, are not rare. They may, in fact, be more common than the conditions that produce a rocky planet with a surface ocean and an atmosphere in which fire is possible. If that is true, then the galaxy may be significantly more inhabited than Drake's equation suggests, and simultaneously far quieter than we have any hope of detecting. Life in abundance. Signals, none. Not because the life is gone, because the life is wet. The recognition problem. Would we even know? Let's go one layer deeper, because the detection problem has a companion problem that is, if anything, more troubling. Even setting aside the question of whether ocean intelligence can signal us, there's a prior question. If we did get into Europa's ocean or Enceladus's or found evidence of complex biochemistry on Titan, would we recognize what we found as life? And would we recognize it as intelligent? This is not a rhetorical question. We have a single data point for what life looks like. Everything we know about biology, every model, every expectation, every instrument we have built to detect biosignatures is calibrated on Earth life. Carbon-based, DNA encoding, oxygen-producing, electromagnetic signal-generating Earth life. When a Europa Clipper's mass spectrometer looks for biosignatures, it is looking for the chemical signatures of life as we know it, amino acids, lipids, specific isotopic ratios that on Earth are associated with biological processes. Footnote 2. This is a reasonable starting point. It is not a guarantee. The researchers who worry about this problem, and there is a genuine academic literature on it, point to what they call the reference class problem. Footnote 16. We have exactly one example of a biosphere. We cannot know from one example which features of that biosphere are universal and which are accidents of Earth-specific chemistry, history, and physical environment. We assume DNA is the universal information storage molecule because it is the only one we have ever observed storing information. We assume carbon is the universal scaffold for complex chemistry because it is the only scaffold we have direct evidence for. We assume life will produce oxygen or methane or some other gas that throws an atmosphere out of chemical equilibrium because that is what life on Earth does. None of these assumptions are unreasonable. All of them are untested on any world other than our own. The orca problem applies here too. If an orca were to develop a signaling system so complex and information-dense that it constituted a written language, transmitted through water, encoded in acoustic patterns, archived in the memories of matriarchal pods, would we recognize it as language? We would record it. We would note its complexity. We might eventually decode enough of it to recognize structural patterns. But would we, on first contact, identify it as the product of intelligence rather than instinct? The history of marine mammal research suggests the honest answer is probably not immediately. Now scale that problem to a world we have never visited, with a chemistry we have never sampled, producing signatures in a medium, dark cold water, kilometers below an ice shell, that our instruments were not primarily designed to analyze. This is the central tension of the sub-series. Stated plainly, we are the measuring instrument. We built all of our search tools to find ourselves. If the universe is full of life that is not us, not carbon-based or carbon-based, but sealed in oceans, or intelligent but pre-technological, or technological in ways that do not produce radio, we are not currently equipped to find it. We might be looking directly at it and not know what comes next and what we actually might learn. I did not want to leave this entirely in the dark because the situation is not hopeless. It is just honest. Here is what the next decade of ocean world science actually looks like, concretely. Europa Clipper reaches Jupiter in April 2030 and begins its flyby campaign. Footnote 2. Its Reason radar will image the ice shell in detail we have never had before. Its mass spectrometer will sample the plumes. Its magnetometer will characterize the ocean's conductivity, a proxy for its salinity and chemistry. By 2034, we will know vastly more about whether Europa's ocean has the chemical conditions for life than we know today. We will not know whether there is life in it. That requires a lander or a submarine. Both are in early development in NASA's long-range planning. Footnote 17. Dragonfly lands on Titan in 2034, the same year Europa Clipper completes its primary mission. Footnote 10. It will fly between more than 24 sites, sampling organic chemistry, the building blocks, but not necessarily the buildings. It will tell us how far prebiotic chemistry can progress in an environment soaked in organic molecules, but separated from liquid water. It will not tell us whether there is life in the methane lakes. That question may require a mission we have not yet funded. ESA's dedicated Enceladus mission, currently in study phase, would target the 2040s. If it launches and works, it will be the first spacecraft designed specifically to look for life in an ocean world, rather than just assess habitability. The plan includes flying through the plumes at low speed, rather than Cassini's high-speed passes, and possibly landing on the South Polar terrain to collect samples directly. Footnote 17. The honest timeline is this. By the early 2040s, if the mission schedule holds, and the funding holds, and the physics cooperates, we will have enough data to say, with reasonable confidence, whether any of these three worlds has the chemical conditions for life as we understand it. We may have tantalizing hints of something more. We will almost certainly not have a definitive answer. Which means the question this episode started with, the orca question, the fire question, the question of whether intelligence that cannot phone home counts as intelligence worth looking for, will still be open. Probably for our lifetimes. Possibly for much longer. The universe is not withholding the answer. It just stored it under a lot of ice. To end on a positive note, right here in our own solar system, within the distance a sufficiently ambitious spacecraft can travel in 6 years, there are at least 3 worlds with liquid water oceans. One of them is actively venting its interior into space and has been handing us organic chemistry samples for decades. One of them contains twice the volume of all Earth's oceans and may have hydrothermal vents on its seafloor. One of them has methane rain and a surface covered in complex organic molecules and a drone on the way. And not one of them has called us. And no, I don't expect there will be a pod of orcas or even orca-like creatures waiting to meet us, but there may be signs of life. But there may be liquid water or an ocean. And since fire requires air, the path from complex chemistry to radio transmitter runs through metallurgy and combustion and a surface with an atmosphere, and that path is not available to anything that evolved under ice. The Fermi paradox asks why the universe is silent. One answer, not the only answer of course, but an honest one, is that most of the universe's life may be sealed inside oceans, living in the dark, possibly intelligent, possibly complex, and completely unreachable by any search methodology we have built. Which means the sub-series question we started with. What if life doesn't look like us? Has a companion question we haven't fully asked yet. What if life doesn't signal like us? What if the galaxy is full of voices and we just can't hear underwater? That is the question that the next episode is going to take apart methodically and with some affection, because it turns out our entire SETI program may be looking for humans in different hats. And that is a conversation worth having. It's a Tuesday. Europa is out there, right now, in the dark. Whatever is or isn't. And that ocean is doing exactly what it has always done, completely indifferent to our curiosity. There's still a lot of universe left to look at.